Hi everyone, in this video we're going to discuss how to solve question 3 of the motion diagrams worksheet, which is about using a position diagram to get a velocity diagram. The hummingbird problem told us that we have seen the hummingbird at various flowers at different regions. To be clear, you have one flower here, and one flower here, where these distances are 0 feet, 10 feet, and 30 feet. And what we have as an experiment is that cameras are pointed at each of these flowers. So those cameras tell us when the bird is there and when the bird is not. And so based on the information in the worksheet, we determined where the bird was at various times. For example, during the time interval from 0 to 0.5 seconds, so the first half second, the bird was at the first flower, which is at the position 0 feet. So the bird during that entire time was right here. But during the interval of a second between time 0.5 and time 1.5, the bird was moving from position 0 to position 30, from the first flower to the third flower. So in order to portray that, we notice that the bird ended up right here at 1.5, at 30 feet at time 1.5, and had to go there from position 0. So the bird went from 0 to 30 in this time interval. Then the bird stayed there for another second. That's from 1.5 to 2.5. That's about a second. And then during the next half second, so this period of time, the bird went from flower 3 to flower 2 at 10 feet. Stayed there for 0.25 seconds, so a quarter of a second. And then over the next quarter of a second, moved from flower 2 to flower 1, from position 10 to position 0. So this position diagram tells us where the bird was at various times. And before we start actually drawing out the velocity diagram, I want to think about an intuition for, like, what's happening between these different intervals. Like, if the bird stays, if the bird has one position, 30 feet, for this entire time interval, does the bird have any velocity other than 0? Like, does the bird have a positive velocity? Does the bird have a negative velocity? And you'd say, oh, no, because the bird's position isn't changing over time. So you could also say, for example, right here, you could probably guess, oh, the bird's position doesn't change during this time interval. So during this time interval, the bird must have 0 velocity. And a similar thing during this time interval. So you can actually read some things from this graph just looking at it. Another kind of thing you can read, and this is a little more qualitative, is you can tell when the bird has a velocity that isn't 0. For example, we know that between 0.5 seconds and 1.5 seconds, the bird is somewhere between position 0 and position 30. That means the bird must be moving during that time. So we can guess that the bird has a velocity. And if we compare this graph, this idea that the bird's moving from 0 to 30 over this time period, and then we look back at our little flower line here, that velocity is going to be a forward velocity. So we can expect that the bird's going to have some kind of positive velocity during this time interval when the bird is moving from position 0 to position 30. We can do a similar thing using this time interval from 2.5 to 3 during this half second period. During this half second, the bird is moving from position 30, so the third flower, down to, or more accurately, leftward, is moving from 30 to 10. 10 is where the second flower is. So the bird can be represented during this time as moving backwards from position 30 to position 10. And therefore, since this is a left direction, it must have basically negative velocity. So the bird has positive velocity here, negative velocity here, and I bet you can guess what the velocity is here, positive or negative. It's negative. So we have an idea of what the velocity diagram that we're going to write will tell us. We know that the velocity here is probably about 0. Here it's positive. Here it's 0. Here it's negative. Here it's 0. Here it's negative. But the real question is, well, how do we determine what those velocities actually were? Now, our experiment does not show us the bird when the bird is in flight. It only tells us where the bird started, where the bird ended, and how long she spent in between those 2 points. So what we need to do is determine a guess, our best guess for what the velocity might have been. And to do that, we're going to use an equation which tells us that velocity. Now note, the units of velocity is length over time. It's how much distance you travel over a period of time, like how far you go. So what we can put in is a length, and we'll call that your displacement. And we'll put in a time interval, and we'll call that delta t. So the length that you travel is, some length, and the time during which you travel is some time, and if you divide those, you get the speed. It's like saying 60 miles per hour. You drove 60 miles in 1 hour, so you actually can write that as 60 miles divided by 1 hour, or 60 miles per hour, and that'd be a way to write velocity. But what we're going to do is actually expand out this definition of delta x and delta t, and we'll write those as the equation x2 minus x1 over t2 minus t1, and that's going to be equal to v. So our velocity is basically what we're going to get from x2 minus x1 is our displacement, how far you went and in what direction, and what we're going to get from t2 minus t1 is how long the time interval was. So we're going to do that step by step. For every time interval that we care about, every time interval where the bird is doing something unique or different, we're going to make that a time interval in our graph, in our table here. And so let's talk about what time intervals are interesting. The first interesting time interval is when the bird's stationary. The next one is when the bird's moving to the third flower. So that's 0.5 to 1.5 seconds. The next interval is when the bird is stationary. So that's going to be 1.5 to 2.5 seconds. The next interval is when the bird's moving to flower 2, which is the interval 2.5 to 3.0 seconds. Then you have 3.0 to 3.25. And 3.25 to 3.5. Sorry, let me write those a little bit clearer so they're easier to see. I just have not given myself a ton of space in these tables. 3.0 to 3.25 seconds. 3.25 to 3.5 seconds. So those are all of our time intervals. And now what we're interested in is what is the velocity during each of these time intervals. And to do that, we want to figure out a few things. We want to know how long the time interval was and how far you went. And to do that, you can either guess from looking at the graph, or you can plug in the final and initial positions. So we're going to first try plugging things in, and then we're going to try guessing. So for the first time interval, from 0 to 0.5 seconds, well, we already know that that's a grand total of 0 movement, but let's plug in everything anyway. A time interval can be described by talking about your starting time and your ending time. Now, our ending time for this first time interval is 0.5 seconds, because that is the later time, whereas 0 is the earlier time. So for our first velocity, 0 and 0.5, we'll plug in the denominator of this equation, 0.5 seconds minus 0 seconds. And so that's going to be our denominator. And that resolves to just 0.5. So the denominator is 0.5 seconds, more accurately. And then we'll figure out the displacement. Now, these 2's and these 1's are said to correspond to each other. What we mean by that is that if you're looking at time 2, there's a specific position at that time, which we call position 2. So at the time 0.5 seconds, time 2, what is the position? Oh, well, the position is 0. What about x1, the position at time 1? Time 1 is 0. According to our graph, the position is also 0. So this is 0 divided by 0.5, which is, as we expected, 0. So we'll plug that into our table of the velocity during each time interval. Now let's do a slightly more complicated version, which is the next time interval. I'm going to erase this. You can always reverse if you want to see it, but we're going to plug in things again. We need to figure out the later time, the end of the interval, and the earlier time, the beginning of the interval. And we've already written that. We've already said, oh, the beginning of our interval is 0.5, and the end is 1.5. So when we plug things into this equation, our denominator will be 1.5 minus 0.5. This is a subtraction. Here, this minus means like, oh, it's just telling us like the interval goes from 0.5 to 1.5 seconds. This isn't a subtraction sign, but here I'm writing it as a subtraction sign because we're in an equation. So our denominator is the later time minus the earlier time. Our numerator is going to be the positions of those two times. So at the later time, the final position is 30. And at the earlier time, the initial position is 0. So this tells us that you traveled 30 feet, because this numerator is 30 feet. You traveled 30 feet in 1 second, which gives us a speed, 30 feet per second. So we have just calculated that during this interval of 1 second and 30 feet, you travel at a speed of 30 feet per second. So let's plug that in, 30 feet per second. Now, like I said before, the next interval, we can just guess. We know that the position doesn't change, so the velocity must be 0 because you're not moving. But what about 2.5 to 3.0 seconds? What about this region? This is the point where we're, instead of using this equation, I'm going to show you how to guess. In order to guess, you need to know a few things. You need to think, how long was this time? And sometimes you can just look at it and say how long it is. For example, if this time interval goes from this point to this point, that must be a 0.5 second time interval. So if we are guessing, what you want to do is plug into this equation. So let's draw a little arrow, and we're going to plug in, for the denominator, 0.5 seconds, because that's how long this 2.5 to 3.0 time interval is. It's half a second long. In the numerator, however, we need to put the displacement. Now, we need to think about two things for displacement. We need to think about how big the displacement is, and we need to think about the sign of the displacement. The size of the displacement is from 30 to 10. So that's this distance on the left here. That's a distance of 20 feet. So that means that the displacement has a magnitude or size of 20 feet. But the question is the sign. What is the sign? Well, we can draw an arrow on our number line representing which direction you went. It was to the left. Or if you see a downward slope, you can guess that it's negative. So we'll just stick a negative sign here. And then we can simply finish by dividing. 20 divided by a half is 40. So our speed in this section is negative 40 feet per second. So let's plug that in. We're almost finished with the table. Once again, we can guess for this interval, it's a 0 velocity because you're not moving. And for good measure, for our final interval, let's do the longer form of the equation one more time instead of guessing. So, what we're going to do, I encourage you at this point to pause and try to do this interval yourself. I hope you paused. And now I am going to do the interval. So we're once again going to plug in into the denominator our final time and our early time. Our final time in this interval, according to this, is 3.5 seconds. That's the end of the interval. So we'll write down here 3.5 seconds. We're plugging that in for the later time. The earlier time is 3.25 seconds. So minus 3.25 seconds. Now let's figure out the corresponding positions. At time 3.5, what's the position? It's 0. At time 3.25, what's the position? It's 10. So we can subtract to the top. 0 minus 10 is negative 10. And in the denominator, 3.5 minus 3.25 is 0.25. You can always check using a calculator if you feel like it. Sorry, and this should be feet per second. Now, once again, we can look and see if this agrees with our guess. We could guess that the displacement is from 10 to 0, so it's a size of 10 feet, and it's down, or it's got a negative slope, so it must be a negative displacement. And the time period is half of half a second, so it's a quarter second. And of course, 10 divided by a quarter is 40. So our final speed that the final velocity we can write down is once again negative 40 feet per second. So now that we have all the information in this table, we can start to draw a velocity graph. So I'm going to take this whole picture, I'm going to copy it, and I'm going to move it down here so we can use the information we have, focus on this right side, and draw a velocity diagram. Now, a velocity diagram tells you what your velocity is during specific time intervals. It can also tell you your velocity at specific moments in time, but I think for this and the homework problem, we're just going to focus on time intervals. So in order to think about time intervals and the velocity during them, we need to think, oh, during a specific time, something is happening. So back in the position diagram, we noticed that from 0 to 0.5, you were standing in one place. So during that interval, we drew a straight line to represent that that was your position the whole time. Whereas during this interval, we drew a diagonal line to indicate that your position was changing. In our current velocity diagram, the way we've written it, we know a velocity during an entire interval, and we are pretending that that velocity isn't randomly changing during the interval. So we're going to guess that our velocities are going to be the same during a given time interval. So to demonstrate that, first let me actually draw the graph. To draw the graph, I know that my maximum value is 30 and my minimum value is negative 40. So I'll draw it here. I'm going to draw it two-sided so I can have a negative side and a positive side. So in our positive side, we'll have 10, 20, 30. And our negative side will have 10, 20, 30, 40, negative 40. 0, and then we'll put in our time, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. So let me just write that in carefully. 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5. Let me erase this and make this better. This is supposed to be 2.5. And now let's use our information to start looking at specific time intervals. So from the time interval 0 to 0.5 seconds, that's this time interval, our velocity is 0. So we're going to draw a straight line from 0 to 0.5, representing that our velocity during that time is the same and it's always 0. Then for the next interval, which is 0.5 to 1.5, as I'm labeling in green here, our velocity is 30 feet per second. And it's 30 feet per second, as we're guessing, the entire time. So we will draw a straight line like this, representing that the velocity is 30 at 0.5, at 1.5, and at every point in between, we're guessing that it's still 30 feet per second. Let's keep going. In the next interval, 1.5 to 2.5 seconds, our velocity is 0 again. That's because we're staying in one place. So we'll once again draw a straight pink line at 0 to demonstrate that our velocity is 0 during this whole time, this whole 1 second period of time. Now let's look at the next interval. During this interval, which can be, here's the green line representing that interval, we're traveling negative 40 feet per second. So, negative 40. This line represents that for this half second, we're traveling at negative 40 feet per second. And then for the next quarter second, which is represented by the green line I'm drawing right now, this is a quarter of a second, we were traveling at 0 speed. So I'll put a little line there that's half the size. And finally, for the last quarter second, from 3.25 to 3.5, our velocity is once again negative 40 feet per second. So this velocity diagram tells us visually what your velocity is during different periods of time. Typically, in the real world, your velocity doesn't instantaneously change. If you're in a car and you want to get faster, you gradually get faster. You don't instantly get faster. In this world, especially if you're looking at a hummingbird, it's going to seem like the hummingbird's velocity changes instantly. So we're going to model that. We're going to pretend that it changes instantly by drawing little dashed lines every time the velocity changes. And these dashed lines suggest to us that something happened. We just don't know what. Somehow, instead of these velocities abruptly changing, there was something that happened in between. These dashed lines are basically saying, I don't really know how they changed. But for the purposes of this experiment, I'm going to assume they changed instantly. And so this last thing helps you get a sense for the path of the velocity. The velocity starts at 0, becomes 30, becomes 0 again, becomes negative 40, becomes 0, becomes negative 40. And this is our velocity diagram. So in order to make our velocity diagram, we needed to know the velocity during specific time intervals. During each of these time intervals, we figured out the velocity by using our position diagram. Sometimes, like in the homework problem, you're going to be told the velocity during each time interval. And then you just make a little table like this, and you plug in all of your time intervals, and you plug in your velocities, and then you draw the graph from that. I want to remind you that sometimes if you want to draw a velocity graph, instead of being given a bunch of time intervals, you'll be given the velocity at various times, just like in this graph. In this table, you have a position at a time. In this table, we have the velocity during a period of time. So sometimes you'll get a velocity graph that looks like this, but in that case, you just treat the table for velocity like it's a position table. Draw the graph like this, but instead of x, you have v. But we won't be doing that in this class, so please don't stress about that. However, in your homework, there is a question where the velocity graph is going to be given to you, and instead of having these dashed lines, the velocity is going to look more like whoop, whoop, so that the velocity itself changes smoothly over time. The velocity is changing, and so that's represented by the velocity being different as time goes on. And it is possible to deal with that situation. You will not draw it yourself at any point during this class, but you will be given some situations like that, and the question will teach you how to deal with those. But don't worry about that too much. This main idea was to teach you how to draw a motion diagram of velocity. I hope this helped. If you have any other questions, please feel free to email me, ask me for a text solution instead of a video solution, or anything that can help you figure this out. And I hope your IAs are also able to help you. Have a great day.